everybody. How are you doing this afternoon? Yeah, we're doing good. I'm Ray. I'm going to be introducing some of the speakers in the plenary over GCAP. And our next speaker is a co-founder and developer at Temple Games, a San Francisco-based studio creating award-winning board games for Android and iOS. Her team is known for digitizing Ascension, Race for the Galaxy, and Roll for the Galaxy, and integrating AI. Prior to co-founding Temple Games, she co-created Cannon Brawl and contributed on The Sims, SimCity, and Spore at Maxis. Please join me in welcoming Theresa Duringer.
Hello. What is it that makes games very replayable? I think personally it's all about offering your players a consistent challenge as their skill level grows over time. And one way you can do that is by offering a competitive AI to them. That's something that my studio, Temple Games, has been working on. We have been integrating neural network-driven AIs to games like Race for the Galaxy, which is a digital adaptation of one of my favorite board games. Oops. Sorry, a second. There we go. All right. So unlike something like a narrative-driven video game, which is really a lot of times meant to be played once, board games are meant to be played over and over and over again. And that's really possible because of robust multiplayer mechanics. But if you're going to digitize a board game, you have to deal with the reality that your players oftentimes want to jump into solo mode because they're exploring the UI for the first time, or they're in a tutorial, or they don't have a lot of friends, or they just don't feel comfortable jumping into the multiplayer pool just yet. So you need to offer an AI opponent to take advantage of those great, robust multiplayer mechanics. So a little bit of information about our team at Temple Gates and why we made Race for the Galaxy in the first place. This is us. We're small. We're just a few people. And something I've learned over the last 10 years of game development is that there are no weight classes in game development. There are no divisions that are going to keep the fights fair. So what I mean by that is that you and your game that you're making, your game is going to be competing with games from vastly different team sizes with vastly different budgets. But there are some things that you can do to stand out and sort of be competitive with those Goliath projects. Your games are going to be sold on the shelf next to theirs, the proverbial shelf, whether that's Steam or the App Store, and consumers don't always know that your game was made with very few resources, potentially. So how can you possibly compete in the ring with them? Well, something we do at Temple Games is we do some little tricks. Our neural network creates its own training data with which to hone itself. We run our AI on a separate thread to keep our performance high, keep the frame rate up, and we conduct the flow of AI events through a series of locking attention tokens. I'll talk through some of these tricks, whether they would make sense for the games that you're working on in this talk. So teams like us, the small teams, we're featherweights, and maybe some of you are too, and that means we're up against middleweights and heavyweights in the ring, but not to mention thousands and thousands of other featherweights. I'm sure that you've heard that 40% of all games that were released on Steam were released in 2016, and it's only gotten sort of worse and worse for us as small developers since then. So it's very easy to get lost in the shuffle. But the good thing about being small is that because you're small, you can go niche. When you're small, your budget's probably smaller. The time investment that you're going to put into a game is probably shorter. You don't need to sell 1 million copies to sustain yourself. So you can choose a niche and really dive into it, which is something that the bigger teams can't necessarily do. So at first, our niche was VR. This is something we had been experimenting in quite a bit. We had some fun developing for the Gear, the Vive, the Rift, and the Go. And the first game that we created was called Bazaar. This is a flying carpet game. It was a really cool sort of roguelike puzzle labyrinth game with procedurally generated content. And it's really fun to explore, but I kind of noticed something when I was working on this game, which is if you've played VR, a lot of people have that experience that like, oh my gosh, whoa, this is so crazy, this is so cool. For me, I wanted to look over at a friend and have that experience. Like if you're on a roller coaster and it's so crazy, you want to look to your friend and share that moment together. And we were kind of missing that because we were doing a single player experience. So in the next game that we tackled, we decided to do multiplayer in VR. And we chose the activity for that multiplayer experience to be a board game, something we all like playing. So we took one of our very favorite board games, Ascension, it's a deck builder, and brought it into VR, and it was pretty cool. You could meet people. I've met friends from around the world playing this game. If you play board games, you know that sometimes your favorite game is not necessarily what your friends want to play, and so it can be hard to find the players to join you in your favorite game at your kitchen table. But in VR, you could play with people from around the world who also find that to be their favorite game. But nevertheless, we did have a problem in VR, which is sort of the dreaded crickets. Anytime you're making a multiplayer game, the worst experience is when you don't have enough people in your multiplayer lobby. There are a few reasons for this. I think that part of it was because VR itself, at the time we've been working on it, has been a pretty immature sort of industry, and the market's not quite there yet. The headsets are quite expensive for players to get their hands on. They might need a beefy PC to run VR. So all of this amounts to friction in getting other players into the game. And so to deal with that, you need to, again, have AI opponents who are going to be there to play your players. So at Templegate's Games, we started with Boardgame AI with Ascension. And Ascension is a deck building game. And for this, we created a Heuristic Driven AI, or a utility AI, some people call them. So that means an AI like this is going to favor moves that we as the developers deem to be superior. These are things like, we say, when you're purchasing a card, maybe choose the card with the highest victory point value on it. Or if you're trashing a card, maybe trash the least expensive card, because it's probably the least powerful. It doesn't matter if you know deck builders. The point is just, we say, this is probably the best move given a scenario. The problem with this model, though, is that if you play board games, you know that the skill lies in the edge cases, when you can sort of gain just a little bit of an upper hand on someone, maybe by leaning into the engine that you're building, or noticing something you can take advantage of in the game. So if we say to our AI, okay, you should always, for example, play all of the cards in your hand before making a purchase into your deck. That makes a lot of sense, because if you play all the cards in your hand, you can accumulate a bunch of currency, buy the most expensive card. Most expensive card is probably the best card. It's a pretty good heuristic. But we might have a really advanced player who sees that their draw pile is low. And in a deck builder, if you draw through your draw pile, you shuffle your discard pile into your draw pile. So a player might see their draw pile is low, they play only a couple cards from their hand, accumulate some currency, buy a card, put it into their discard pile, play another card which causes them to draw, which causes them to deplete their draw pile, which shuffles in their discard pile with that newly purchased card into the draw pile, play another card that causes them to draw, and have a chance at drawing that newly purchased card. It's a kind of a complicated scenario, but a move like this could win you a game in a board game. And these are the kind of moves that really sophisticated players can accomplish. And if our AI is not doing them, it's not going to quite keep up. And our AI is not doing them. We could capture that scenario with our code, but if we were to capture every single scenario like that with handwritten code, it would become extremely overwrought. It would be big, hard to maintain. So we don't do that. And the result is that sometimes the advanced players can kind of blow through our AI. So with Race for the Galaxy, we chose a totally different model. A little context on this game, Race for the Galaxy is an engine builder card game set in space. You build cards into your tableau. This was designed by Tom Lehman, and my team has adapted it for digital platforms. We adopted it too. So when I was working on Ascension, I still loved playing lots of board games. The people at my company met through a board game club. So I was Googling one of my very favorite board games, which is Race for the Galaxy, to see if I could play it online with my friends. And I didn't find any version of it on the App Store or on Steam, but I did find this AI research project, open source, on the web. It was at keldon.net/rftg if anyone wants to check it out. And I started poking under the hood. Now, this neural network was created in 2009, which is 10 years ago. In the last 5 years, we've really seen neural networks explode in the fields of natural language processing, computer vision, autocorrect, delivering ad content. But 10 years ago, Keldon was applying neural networks for Boardgame AI and doing a pretty good job of it. So he had worked on games like Race for the Galaxy, Blue Moon, and Descent, all with this neural network approach. So I was poking under the hood, trying to see what he was working on. There was a client you could play, and maybe some of you have played it, it's pretty great. And there was a feature that I really wanted, which was I wanted an alert when an opponent had taken their turn. And I started thinking more and more about the features that I wanted to see, but the biggest thing I really wanted to see was mobile support, so I could take this with me on the go. So I got in touch with the designer, Tom Lehman, and he invited me to this cool board game night with cool people like Don Woods, who made the original adventure game. And I pitched him on making Race for the Galaxy, and he said I could, but he had one request, which is that I check out this guy, Keldon Jones. Apparently he had made a pretty neat AI, which I was a big fan of. So the AI that Keldon created was based on TD Gammon from Gerald Tesoro, who is a researcher at IBM. And TD Gammon is a pretty cool AI that was based on a 5,000-year-old game, backgammon. So Tesoro ultimately pioneered an AI that changed conventional wisdom on how best to play backgammon. This AI came up with its own unorthodox strategies that have since been adopted at the highest levels of tournament play around the world. So just an example of that is the slotting versus splitting. Traditionally, if you're playing backgammon at the highest levels of play and you rolled an opener of something like a 4-1, you would traditionally move your 6 checker to the 5 slot. That's, I think, because if they don't knock it out, you're in a pretty strong defensive position. So that's been thought of as the go-to play. But what TD Gammon discovered using the neural network is that splitting, using that 1 dice to move the checker from the 24 to the 23rd slot, was more effective. Now, it's not clear to me why this is a better play necessarily. I think that neural networks a lot of times are these black boxes. We don't know why something is a better play or not, but we can look at the success rates. So slotting, the conventional method, was predicted to have a slightly lower score towards winning the game, and it turns out the predictions bore out that it did have a less successful win rate than splitting. So how is it that this AI can discover the superiority of a strategy that 5,000 years of human expertise has not been able to figure out? It's because it's using a network that's free of human bias. So typically, if you want a neural network to be able to identify photos of cats, you're going to feed it a bunch of photos of a cat that a human has said, this is a cat. That's the training data. It's really expensive. It requires human labor. Keldon's AI does something different. It's based on a teacherless system. So the AI from TD Gammon and for Race for the Galaxy starts with 0 initial knowledge. So unlike our heuristic AI that we were creating for Ascension, where we pre-populate it with all of these imperatives, there's none of that going into it. And that's good, because as we've seen, that human expertise can be fallible, like we saw with slotting and splitting. So a neural network typically gets better by adjusting the edge weights so that for a given input, the network's output better matches the training data. But we have no training data, I said, at least not externally. So how can we train our neural network? Well, it trains simply by playing itself. The network is fed input, produces output, and receives a reward signal based on a feedback signal. That feedback signal is not coming from external training data, it's simply coming from whether the game was won or not. So you can just look at the score, you can have AIs playing against each other, and you can see when the AI won, and favor those strategies in your neural network. And so that's how it learns and grows. So not only are we able to see whether a strategy won, but we can also see by what margin. So if it won by a landslide, we can say, okay, this was a really good, and we can hunker down on the edge weights that we've already established in our neural network. If we lost by just a hair, we can favor away from the current edge weights. So because of this, you can generate virtually limitless training data with very little human expense. So what does it actually look like with our neural network structure? Some of you might be familiar with neural networks, and this is going to be kind of basic for you, but it'll be very quick. So for the input for our neural network, it's 800 different nodes, 200 per player. This is basically just describing the state of the game. So is X card in Y player's hand? What are the cards that you know of in the discard pile? Are there any goods on any cards? It's a production game, so there's a concept of goods. Just anything that describes the state of the game. This is the input that we put into our neural network. The output is how likely is a player to win? And on turn 1, you might imagine that every single player has an equal likelihood of winning. So they all start out at a 25% chance of winning. So at the end of the game, one player has won, so they have a 100% chance of likelihood of winning, and everyone else has a 0. So this is the output that we're expecting from our neural network, and on every single turn, that number is going to be somewhere between that 25% and that 100%, hopefully, if you're the winning player. Now, the input's on the left, the output's on the right. We have a single layer of 50 hidden nodes. We don't do anything too deep here, and we have a complete graph of edge weights connecting all of these. So hundreds of edge weights to adjust. And the way that we adjust the edge weights, which is how the neural network is learning, is by plugging our outputs into a formula. This is the formula for TD Gammon. We use something very similar at Templegate's games. So don't worry about writing down any of this math or anything, but just to understand some of the relationships of what's happening here, we plug the outputs from our neural network, y sub t plus 1 minus y sub t, that's the outputs from a turn to the next turn, into the network. And what we're trying to get out here is how much we want to be adjusting those edge weights from turn to turn. And then we have alpha, which is just an arbitrary learning parameter. In our case, it's 0.1. Grad W is how much changing a particular weight is going to affect the output value. Sigma is sort of like a for loop stepping through the turns to initialize k for lambda. And lambda is an arbitrary decay. In our case, it's 0.7 for a turn, and it sort of multiplies as you step back through turns. And what this is doing is it's saying that it's training the neural network on earlier turns than just the last turn. So if you get the final reward signal, whether you won the game or not at the end, when the game is won at the very last turn, you can still propagate some of that information to previous turns so that the neural network can drive your AI to make smart decisions as early as turn 1. And it's got a little bit of a decay on how much it affects the decision making. But this isn't the only way that we can train our neural network to be making smart decisions as early as turn 1. Something that Gerald Tesoro also figured out is that you can supercharge your neural network by training it on every single turn, not just waiting till the end. But the big question is, how can you train it on every turn if you don't have that final reward signal on every single turn? You don't know if the game is going to be won or not. Well, you have something else rather than if the game is won or not. You have a prediction of whether it would be won or not, and you can get at that with the neural network itself. So you can run the neural network to generate sort of a prediction of who won and train it against that, and it actually turns out to be very effective. So this is kind of what it looks like. On turn 1, you plug your inputs of the game into your neural network. You receive your outputs. You plug your outputs into the formula. Your formula tells you how much to adjust your edge weights of your neural network. Now your neural network is different. You can skip to turn 2 and do the same thing, rinse, lather, and repeat. And because of this, our neural network has, even though it's only trained on about 30,000 games, it's gotten about 1 million training events from this turn-by-turn training. And it turns out that this makes it very effective and that the AI can be a really good player. So using this knowledge-free system frees us from relying on a human teacher. The AI only needs to know the rules of the game. And this is really interesting for 2 reasons. One, it keeps our costs really low. So we can generate virtually limitless training data with very little human expense. And 2, it frees us from human bias, which has been a big controversy for AIs recently. So as opposed to the heuristic driven AI, the TD-Gammon version is not hampered by what players conventionally accept as the correct moves. There's no dogma about what are the superior moves, so it's able to discover new strategies. And these strategies can propagate back to the player community. Something I've seen with Race for the Galaxy is that the AI plays very differently than people do. People tend to follow a color in this game if you've played it. And that can be a strong strategy, but the AI, it doesn't have that same sort of like allegiance to a particular color, and it tends to be more effective at playing the game. So people who have played against the AI, you can see their play patterns actually following what the AI does a little bit more, which I think is pretty cool. So because there are no heuristics, the initial strategy is going to be pretty terrible, but this kind of neural network has really good scaling behavior. So we see that within the first 1,000 or so games, tactics are going to start to emerge. And what's really cool about what we're seeing is that these tactics are really context sensitive. So you might have a scenario where in Ascension, in our old kind of AI, we might have said, well, buy a card that has a really high victory point value, because that's always good. Victory points are good. With the neural network version and the context sensitivity, you might say, well, on turn 1, maybe it's not good to buy a high victory point value card because it's expensive, and that's going to hose out my economy, and instead maybe I should be investing in my engine. So the AI is able to like pick up on some of these really cool tactics that humans can do too. So also it can recognize that moves are not necessarily always good or always bad, that context really matters. The other thing that it does is it frees the AI from being capped by our skill level as developers. When I'm telling the Ascension AI how to behave, what are the heuristics, that's just based on my own personal skill at playing the game. And I'm certainly not the best player in the world. So when you have something that initially starts with 0 knowledge, it can then surpass the skill level of the developers who are making that AI. So I've been talking a lot about the neural network that we ship in Race for the Galaxy as if we ship one neural network in there, but in reality, Keldon bifurcates the model, and we ship with 12 different neural networks. Each of these is a different tailored neural network to specialize for a certain configuration of how many players there are or how many expansions there are enabled in the game. And the reason that we do this is because this kind of neural network works really well when you have a fixed number of inputs. So if you're having a game run the 2-player neural network, you don't ever have to deal with any kind of input about a 4-player game. So you need to figure out for your game, if you do apply this model, where you're going to architect your bifurcations, because you could continuously partition your neural network, but you're going to see diminishing returns, and you're going to become burdened with complexity and size, which is bad. Our neural networks in our games end up being about the quarter of the download size, which is actually quite large considering that we do card games, which have really large art files. So, and we don't actually just ship with 12 neural networks. We actually have 2 different main functions. So your neural network is really just a function trying to produce output. And the one I've been talking about this whole time is what we call eval board. It generates a score based on the goodness or how likely a player is to win. But there's another function that we have, which is why we ended up shipping with 24 different neural networks, which is called eval roll. What eval roll is doing in our games is predicting what the opponents are going to do on their turns. What move is player X going to make given game state Y? It's really important when you're playing a board game to be able to predict what your opponent is going to do, more so for some board games than others, because this is the key to winning. So the neural network AI uses this particular function. In this case, it's chosen to trade a good, and you don't need to know Race for the Galaxy, but it's chosen to trade. And a lot of new players would probably write to me an email saying, oh, there's a bug in the AI, this is not working. It chose to trade and it doesn't have any goods to trade. That's a dumb AI. But actually what it's doing is making a prediction, I think. Again, it's black box, so this is my hypothesis. It predicted that I was going to choose settle successfully, because I did choose settle, that's me at the bottom. And when I settle, it gets to settle, and it can settle a world, and that world can come with a good, which is what happened, and it could trade the good. It got 2 turns out of 1. So it can develop things like piggybacking. This is something that our heuristic AI couldn't really do. So what does it do with the predictions? It plugs them into a simulation, walks the game forward in a number of directions, and runs eval board on each of those directions, determines what's the best one, and that's the move that it's going to make. So with this neural network, are we continuing to train it? Are we, the game is live, it's out there on the App Store. Are people's decisions factoring into what the AI does? No, for us, we don't find that that's necessary. We find that the AI is still competitive against even the best players, having only played against itself. That's just a question sometimes people have. So if you're curious for your own games, you don't necessarily need to do that. So the result of everything that I've been talking about today is that the AI is really hard, or at least it can be. And you might say, hey, Theresa, cool, but is that really fun? If I'm a new player and I don't know the game, do I really just want to be completely pummeled by your fancy hard AI? And you're right, it's not fun. But it's a lot easier to make a hard AI into an easy one. The reverse is not true. So what we do in this case is the AI is making decisions based on the score, the output. We introduce a little bit of noise to the score, and we can tune the amount of noise that we put so we get the right rate of difficulty. So we want our AI to, for example, a medium AI to win about 25% of cases against a hard AI. And it works out pretty well. So once you've created an AI, another thing that you have to do is communicate what is that AI doing so that your players have a sense of what's going on in the board game. And this has been a big problem. I've seen a lot of board game apps out there tackle it in different ways. The most common thing that people do is anytime the AI takes an action, they animate exactly what happens. The AI drew a card, they animate that. The AI discarded something or gained a victory point, they animate that. The problem is that it can be mind-numbingly tedious to watch these animations. And also, you don't really get a sense of what's important and what's not in the game. So a lot of developers deal with this by offering a slider where you can make your board game app AI faster or slower. The problem is if you make it really fast, you really can't see what's going on at all. So you miss out on all the interesting bits. So we've been thinking a little bit about what are you really trying to communicate with these animations that show what the AI is doing? And I think you're really trying to communicate state changes of the game. Who's shuffling their cards? What's going on? Who's taking over what? In Race for the Galaxy, it's a simultaneous action game. So communicating what all of the players are doing in a four-player game where people can be taking over worlds and just doing all kinds of stuff. This is what I feel like as a UI person. I feel like I am at this crazy traffic intersection and I've got my whistle and I'm just trying to make some sense of it so that it's digestible to people and nobody crashes. So the system that we came up with is a series of locking attention tokens. And all this is we say, basically, there's a hierarchy of attention tokens, the top one being the main attention token. If something really cool and big happens in the game, like an AI takes over a world or destroys a world, we say, all right, that event grabs the main attention token, and no other main event can happen right now. We'll queue them up behind. But at the same time, minor events, someone got a victory point, someone discarded a card, can still continue. So we sort of divide up our animations of the events in these separate threads that have different priorities. And it works really well to communicate what's going on. One reason we can do this is because we have a custom engine, and that gives us quite a bit of control. So in Race for the Galaxy, we see our neural network making upwards of 500,000 evaluations to the neural network on a given turn. So it helps to be able to tightly control performance and memory. We also have finer grain control over the clocks and the timing in the game, which is important for the user experience. Communicating your AI's actions through a system like the system of locking attention tokens can help manage the flow of information to be more digestible for them. They're not necessarily going to know why, they're not going to know, that you're running things on a different thread or you have locking attention tokens. They're just going to know it felt good and they're going to come back and play, which is why we see people playing like 6,000 games in a row, which is kind of crazy. So, I've talked all about how great this kind of neural network is and you should totally put it in your games. But the sobering fact is that not every game is a really good candidate to do a network like this. So here's a little bit of a checklist to see if this is something you might be interested in. Are you working on a board game? Board games are great candidates because they require complex sophistication to play, and the rules are really, really well defined. Discrete rules are really important to make an AI like this. Is your game have a lot of randomness, high stochasticity? That means you've got dice rolling, deck shuffling. This randomness means that there's going to be more space to explore, which means your AI can be discovering novel strategies, which is kind of interesting. Also, games like Race for the Galaxy with lots of randomness have high branching ratios of possible RNG variables, which means a deep search method like you might traditionally see with chess or checkers is not going to be feasible, even with a supercomputer, let alone your dinky little phone. So you need to use a different kind of AI solution. So what is a neural network? It's basically a black box that's trying to emulate a function to get outputs to better match training data. So using your non-deterministic games here results in a smoother function. Small change to the input is going to result in a nice small change to the output, which is easier for the neural network to learn. So that randomness in the game is actually really helpful for that smooth function. So here's a counterexample. Lots of games have there's importance to the spatial relationships between the pieces. Games like Othello, chess, checkers, and Go have canonical patterns and configurations. This is chess, and this is Sea Cadet's mate. It's going to mate in 10 moves. If you can imagine a small change to the input, the game state, maybe that knight is 1 square over, that's actually going to result in a pretty large change to the output, the likelihood of winning. So this kind of game with these spatial relationships like this is not a good candidate for this kind of neural network. Also, you want games that have a defined terminal state. So backgammon is really great. You're rolling dice. Those dice are just positive numbers. You're always advancing in this counterclockwise way towards the end of the game. You're eventually going to hit the end of the game. if you have a game like chess, not to bag on chess, it's just not a good candidate for this. You could have a scenario where you move a piece, your opponent moves a piece. You move a piece, your opponent moves a piece. And you can go in this sort of like stalemate dance, which can result in no ending, which means if you have no ending, you have no final feedback signal with which to train your neural network. So you really want to have a final end state in the game. Now, Race for the Galaxy didn't have that. If you know Race for the Galaxy, you know the endgame condition is you need to run out of victory points, or one of the players has built 12 cards in their tableau. So you could imagine a scenario where there's 2 AI players, and they're just exploring and drawing cards over and over. In that scenario, you never get the final reward state. But you can just introduce like fake rules, like nobody's gonna know, which is what we do. So we just introduce a fake rule, which is the game ends at 30 turns. So when we're training our neural network, at 30 turns, if all your AI has done is draw cards at 30 turns, did they win the game? No, they didn't. So your AI is gonna stop favoring that strategy and it's gonna learn. While you could theoretically make a temporal difference neural network for a co-op game, and it could be kind of interesting to figure out how to make a companion that helps but is not too helpful, you wouldn't want to choose a game like One Night Werewolf. And that's because the crux of that temporal difference learning is the successive training based on predictions over a series of turns. So you can't use a game that only has one turn. And in fact, we see that the acumen of the AI kind of falls off towards the end of the game, because at the beginning, it's benefiting from a lot of turns with that lambda decay factor affecting the decision making at the beginning of the game. So finally, it's really good to find a game that has an existing fan base. Board games work really well for this because a lot of times if you're making a digital adaptation, it's because it's based on a popular game, which means there's probably a big fan base. So for us, we release our betas on Board Game Geek, and we get people who are the best players that we can find playing against our AI, which is just really good in helping identify bugs. You know, the AIs might be crushing each other, but until they're playing against a really good player, that's when you know if they can beat that benchmark player, that your AI is any good. And a lot of times those bugs, if you find them, are going to be in the simulation, so that's helpful. So for us, after we released Race for the Galaxy mobile, we also did a VR version of it because we like doing VR board games, they're kind of fun. And that's a kind of neat area for research opportunities. In VR, you can bring the AI to life by having them occupy an avatar, and that avatar has animations. So you can use those neural network scores to inform the animations that your avatar is doing. If your neural network is predicting a certain player to win, you can use that to have that player have gloating animations, or if someone's more losing, you can make them look more dejected. And we've been looking into more of these research opportunities with AI. Right now we're working on Roll for the Galaxy, which is its own interesting challenge because if you've played that game, it's a dice version of Race. It has a lot of dice, which means tons of RNG variables, which means the search space basically explodes, which means we can't really process through all the possible outcomes. We have to do some slick tricks to try to cull down our search space to make it performant. And we are trying a two-pronged approach. We are looking at AlphaZero to use neural networks, very meta, to then prune our search space. And also we're looking at using dice probability math to just use human knowledge. In any case, maybe I'll have more to talk about that later when we figure out how to do it. And so that's Roll for the Galaxy. And so basically, 20 years ago, it wasn't necessarily clear what the practical applications of temporal difference AI was going to be. But as board games become more and more popular, I think that this kind of AI is going to take off. It's really helped us as a small team. It's given us the tools to be competitive against bigger teams. A lot of times if you see indie games out there, they use things like procedural generation to extend what they can accomplish as a really small team. They don't have, a warehouse of artists cranking out beautiful art for them. They reuse things to extend their game, and we can do a similar thing with this type of AI. We can extend the replayability of the game using algorithms. So hopefully this is helpful to some of you. This is Gen Con. There were 80,000 people at this convention. It seems like board games are becoming more and more popular, so I hope that more people make board game apps. If anyone makes one here, I'd love to play it. I'd like to see if anyone else is working with AI like this, and that's it. Thank you for coming to the talk. I don't know if we're doing like a QA session. Maybe I should do a QA. Yes? Okay, does anyone have any questions? Yes? No, but if you like to talk to me about how to make this better, I would totally love to hear. Yep. And this is my Twitter handle. So if anyone has ideas on how we could be doing this better, please tweet them at me. I would love that.
So for the hyperparameters for the algorithm, things like the learning rate and the discount factor, and the number of nodes, the network, and so on. Did you search systematically for good values for those, or how many trials did you have to run to figure out the right values for those?
Well, I mean, the honest answer is I didn't have to run any. This is really the work of Keldon that we integrated into our thing, and he had refined this basically 10 years before we even started integrating it into our board game engine. So I'm sure he can answer that. Yeah, I don't know how long he spent refining those figures.
Do you run into any issues with overtraining? And given that the AIs are training against other AIs, you'd think that they would develop really good strategies for beating the strategies that the AIs themselves are using, but not necessarily the meta that the players are using. So were there any issues with the strategies that the AI using being less effective against the strategies that human players were using?
Yeah, I do believe that was the case, and I think that there was some nudging after those were happening, some nudging to push things away, and yeah, I think that has happened. I don't see any other hands.
We have about 5 minutes.
All right.
Do you have any good resources for people who want to look into neural networks and that sort of stuff? Any good learning resources for people who haven't really gotten into it before but want to?
Yeah, I know there's a book coming out pretty shortly by Ben Weber, and W-E-B-E-R, and he's doing sort of a survey of a lot of this kind of information, and I think that's going to be, I've read some of the preliminary stuff, and it's going to be really good. I recommend that.
Hi. As a small developer, are you mostly looking to digitize other board games that will fit with the model that you've created, or has the studio sort of at a point now with the success of Race for the Galaxy that you can start to venture towards other board games where this machine learning model doesn't really suit?
Yeah, that's a good question. And more sort of in line with what I'm doing on a day-to-day basis, with the figuring out what we're going to make next. Certainly, now that we've invested in this so much, we are definitely paying attention to how well a board game would match up with this system. And you know, we did another board game since Race for the Galaxy, which was called Shards of Infinity. It was the sequel to Ascension. And we sort of hybridized our AI approach. So for the very hard AI, we did a neural network like this. And for the easier ones, we ended up using a hybrid one. So I think it's a kind of case-by-case thing where if we see that the board game has so much value that it's worth kind of more of an unknown or having to put more research energy into figuring out a new kind of AI strategy. If the board game's amazing, then yeah, I think it's kind of worth it. But certainly now that we know that this works, it's fun to try to identify games that this will just sort of like map really well to without putting a lot of effort in.
I was just going to ask, because you guys said that you were a small team, how much was the infrastructure, I guess, to set up the neural network? And like, is it feasible for small companies to, I guess, spend the hardware to run the neural networks, and how long that takes?
Yeah, I guess part of that really depends on sort of how expensive it's going to be to train your neural network. So with us for Roll for the Galaxy, that turns out to have those higher amounts of RNG, we really ran out of resources on our own computers to do the training. We then sort of magically, timing-wise, got accepted into a Google startup cloud program where they just give us compute credits, which we're using now. So, you know, depending on sort of like the financial resources, I guess that might affect whether you're going to jump into this. I wouldn't say it's sort of like talent limited as much as just like the processing, the training expense.
Hi. Given the provenance of the solution you guys came up with, are you planning on open sourcing parts of your own solution?
Certainly something we've thought about, and I think everyone on the team is open to it. There's just sort of like an expense to putting something out there and maintaining it. We've thought about that with our custom engine as well. It's just hard to, you start shifting into like sort of being a software service type of job, which we all sort of left and tried to hide from, and but certainly it's something we'd all like to do if we had extra time. And also, like, if you like I mentioned, Keldon.net/RFTG does have an open source version of the Race for the Galaxy AI, so it's certainly a great resource if you're interested. I think that might be it.
That's time, so.
Great. Thank you so much.